All right, thank you. Okay, so today I will focus on setting up a framework to understand the model stealing attack and defense. Okay? And this, as I mentioned, is joint work with my former colleague, Professor Jeding at University of Minnesota, and PhD student we jointly supervised, who is currently a postdoc at University of Chicago. All right. So as we all know that AI has been transforming our society, and one concern is, privacy. And Tony talked about privacy from the data or algorithm perspective. Here we want to explore slightly different concept, that is how to protect your model when it is used to provide a service. Okay, so that's the main thing we want to. Wait. All right, sorry. So which one? This one, right? Yep. Okay. So in the age of AI, a number of important issues are there in order to have a trustworthy, AI product. And some of the key elements include privacy, okay, security, explainability, as well as fairness. Okay. All right. So these aspects are emphasized, for example, by presidential executive order, right? A couple of years ago, as you can see, the highlighted words, okay? Safety, security, privacy, equity, okay? All these are important. We really want to take advantage of big data to help the society. All right. So the computer is a little bit slow for some reason. Now, with the generative AI, we can do a lot of stuff, right? The large language model, has been so successful, and everybody perhaps has benefited from writing a code or generate some image or video, right? Those things become, easy task. And trustworthy of AI, is really important in some safety critical applications. Okay, for example, auto driving or medical diagnosis, for those settings, if a model is attacked by adversarial, that can really cause a lot of trouble, right? So therefore, it's important to study these issues. So our focus today is what we call model privacy. So it's our first effort to understand how well and how you can protect your model. So let's assume you have collected your data and you build maybe a diffusion model, whatever, okay? And your cost of building the model is quite significant, 600,000 for instance, okay? And then you deploy this model, on the internet. Okay, people can pay, and then we can do prediction, for example, okay, for the customer. And suppose you have an attacker, okay, and he will pretend to be a customer. And then he asks your service, okay? And if we are not careful, as we will see, then the person can reverse engineer, okay, and then learn your secret model quite easily, right? And his stealing cost can be maybe just $1,000 to get almost as accurate, prediction algorithm as you, okay? Then that would be tragedy for your service, okay? Not only they do not need to, pay a fee to you anymore, but also they can become your competitor, right? Offering similar service. By the way, this is work currently under revision, for a major journal. Okay, so here is a really simple example to make the point very clear. So for instance, suppose we have a classification task, and we use logistic regression. Okay. As you know, in this parametric model, we only have a few parameters, possibly maybe 100, 200, but still a relatively limited number of parameters. And then if the attacker request, okay, different individuals, okay, and want us to give the predicted probability, how likely the person has certain disease, okay? If we don't do any protection. Obviously, with as many cases query as the number of parameters, the attacker can exactly figure out what the parameters are, and your model is completely at risk, right? I mean, not only at risk, but is stolen by the attacker. Does that make sense? Okay. All right. This is a simple example, but more generally, we have this framework. So we have the victim model. That's the model you use, okay, to provide predictions, okay, for your customers. And the attacker, okay, pretends to be a customer and then interact with you. So he sends queries and you provide predictions, okay? And then he will reverse engineer to get the model as accurate as possible, okay? So more generally, so they can abuse your service in somewhat different ways. One is, as I just emphasized, rebuild a model, okay? And hopefully the accuracy is very similar to yours. Okay, that's one possibility. Or maybe they want to steal your model structure. You want to know how you build the model, what kind of neural network structure. And perhaps also facilitate their own training tasks in some way. Okay. All right. And there has been a lot of work actually on model privacy. There are different emphases. One is model attacks, okay? And in classification case, as you can easily imagine, where you want to send the query. So what kind of X you ask this model owner to give you prediction. That makes huge difference, right? Turned out it's much helpful to the attacker to send queries that are close to the decision boundary. That's where they gain most. Okay, that's one type of work. Another is from model defense perspective. So there are two types. One defense is that you say, well, let me just try to figure out whether you are a normal user or you are adversary, right? So by checking the query distribution, whether that's similar to the regular users, then they have some idea. So that's one way. Another, of course, is to add noise. We gave perturbation, and that is the one we're going to focus today. Okay, all right. And looking at the literature, although there are many fantastic examples, we feel that the results are still somewhat limited in the sense that algorithms are heuristic. There is no theoretical understanding. And the evaluation criteria also seem to be a little bit informal in some sense. Okay, so the bottom assessment from our angle is that the theoretical setup is still not quite there. That's why we want to put initial effort on this. Okay, that's the background. All right, so we want to provide a mathematical framework to understand model privacy. Okay, so we have two players, okay, attacker and defender, okay? And then there's the action, of course, the attacker would send the query, okay? And the defender would provide prediction, right? That's the actions. And afterwards, the attacker will try to learn, the model, okay? And they have different goals and different ways to evaluate whether they are successful, okay? So the theoretical questions we want to understand, is it necessary to defend your model? Maybe you don't have to, okay? And also quantify the effects of the existing possible defenses, and perhaps also finding out what is optimal defense. Okay? And one important point is that in the defense of adding noise, okay, to the prediction, we need to make sure the noises we add are dependent, not the traditional, independent noise, as we will explain more later. All right, so let's set up a little bit more carefully. Okay, so on one hand, okay, there is the attacker. Okay, his goal is to estimate f star. So f star is a regression function or classification function we want to protect. Okay, we have already learned that through huge effort. Okay, so attacker try to get f star as close as possible, and the actions two types, right? One is query. You send different xi, okay, and you receive yi tilde. We use yi tilde to signal that we're going to protect, right? We're going to add noise, not exactly the actual f star at xi. Make sense, right? And once he receives, query response pairs, then he will try to rebuild, f star, and the estimator is f n hat. Okay? And we have the evaluation criteria we call LA to emphasize its attacker perspective, right? For example, the attacker may want to steal the model for young people instead of for general population, right? So therefore, the loss function, can emphasize that. Okay. So two things are critical: query strategy and then learning algorithm. What kind of X should I ask? Okay. And how do I learn once I receive the response query pairs? Okay. All right. From the defender perspective, right, we want to prevent f star from being well estimated, okay, while providing good service. Okay. So the action is that once we receive xi, we're going to return yi tilde, right? We want to add some noise, okay? Otherwise, as we already see, the model may be stolen quite easy. And then the evaluation criteria, we put LD to emphasize, well, from a defender perspective, I may have a different goal, right? So I may care about certain, more important area than others, which may differ from the attacker. Okay, so the core thing, defender is thinking about how should I defend in our context? How should I add noise? Okay, to the actual f star value. So far, so good. Okay, very good. All right. So let's see, how do we really quantify the goodness of defense? Okay, so we thought about it that, Professor Chen is here. Okay, so we're from economic perspective, right? That seems to make sense. Okay, although in the end, we're going to go back to the risk perspective that Professor Tsai talks about. Okay, all right. So the economic perspective seems to be natural. Okay, in a parametric model case, a finite number of queries would suffice, right, to steal the model completely. Okay, and if we add ID noise, okay, so here's no defense, okay, easily steal the model. If I add ID noise, and if you, for the attacker to achieve the accuracy epsilon, okay, so he needs to have this many queries, right, from a standard, linear model theory or parametric model theory, okay, right? And our goal is, to devise, another defense, okay, not the ID noise, so that, the cost is much higher in terms of you have to send a lot of queries, right? Therefore, pay much higher price to learn to the degree of same accuracy, okay? So that's what we try to accomplish, okay? All right, so how do we make it more mathematical? Well, we can define, right? So we already have the loss, okay? And then we can talk about risk. So if you want to achieve the risk, to a certain degree, epsilon, okay? So how many queries you have to send to do that? Let's call that the necessary stealing sample size, okay? All right, that seems to make sense. And then we can define attack strengths. You see, the attack strength is to compare. One way, I send query, you give me, okay, response, and I learn. Another way is I just go out and collect my own data, and then I rebuild, the f hat, okay? So we just want to look at the cost, okay, the ratio, okay, and we call that attack strength. If this ratio is bigger than 1, it seems it's more, cost efficient to steal, right? than building the model myself. Okay, so therefore it's an economic perspective. And as you see, the essential thing is still the risk. Okay, because we want to achieve risk to certain accuracy. Okay? All right, and defense strengths can be defined similarly, although, as I said, defense and attacker may have different perspectives, right? So their loss functions can be different. Therefore, the quantity are not necessarily the inverse of each other. Okay. All right. So now we have forgotten one important aspect. We have to make our customers happy, right? So therefore, that's the utility loss. Okay. So we define utility loss, to be the actual value we hope we can provide if there's no, model stealing at all, to the actual, response, so the discrepancy, how much, damage we have provided, okay, for the prediction. Okay, does that make sense? This is the average. We call that the utility loss. So if we don't do any noise addition, of course, the utility loss is just zero. Then everything is good for the customers, but we risk our model being stolen. Okay. All right. Yes. Yes, you already have your F star. Yes, we are protecting that model. So we'll start from there. You already have done your learning. Yeah.
In the beginning, is there some F star that's easier to learn and some other F star that's more difficult?
Yeah, I think so. So later we're going to consider different classes where F star belongs to, and then we're going to see. Yes, very good question. Okay. All right. Any other question? All right. So the things we're interested in, right? When is it necessary to defend a model? So what is the best defense mechanism in whatever way you mathematically quantify? And what kind of attacks are easier to defend? We can ask a lot of questions, and we want to have a framework to understand this. Okay? And there are some technical challenges, seems to us. One is that, as I emphasized, if you add independent noise, that's not a good idea, which I will explain a little bit more. Okay, but you can already imagine. Okay, so how do you introduce dependent error? That's not necessarily trivial. Okay, all right. And second is that utility loss. Okay, we want the utility loss maybe to go to zero as the query number n goes to infinity, because that means that for people relying on your service long term, you do want your accuracy to be better and better, right? Otherwise they will be unhappy. If so, this is different from the traditional statistical learning where we assume sigma squared is fixed. Sigma squared doesn't go to zero. Turns out there are some tricky issues which we haven't completely understood. Okay, at least generally. Okay, all right. So, what are the most important quantities we need to highlight to provide a solution? First, of course, F star. So, as Professor Tsai already hinted, so you're gonna maybe model F star different. There's a possibility. So we assume F star belongs to a class F, which is a tradition in statistics, right? Okay. And M is for defense mechanism. Okay, we assume M belongs to a class. The class may include all possible defense or certain type of defense. Okay, for example, ID noising. Okay, and then for the attacker, Q is for query. How do you query? The ID query, or some other fixed design, or sequential. So we will discuss more later. And then T we use to denote what learning algorithm the attacker is using, right? Once he receives the query response pairs. Okay. All right. Okay. So now here is the core definition we have. Okay. The core thing we want to understand. So we define model privacy. Okay. So we define model privacy. So let's see what this means. Well, we are model privacy here. Is given a query strategy and given a learning algorithm of the attacker. So we are conditional on that. Okay. So we already know, Well, at least for the definition, there is a query strategy and there is a learning algorithm, okay? And then we're talking about the model privacy, of a specific, defense mechanism, okay? Therefore, it's a property of a specific defense mechanism, okay? But the background is the choice of query and learning strategy. So what is it? Well, you see, because F star can be any member in script F, then therefore we look from the traditional minimax perspective, right? So how well can the attacker learn the two F star, okay, in my class uniform, okay? So that's the quantity. And then the inf is now over the query and the learning strategy of the attacker, okay? So maybe let me restate, okay? So for a given defense mechanism, okay? So you have a defense mechanism, okay? And suppose the attacker can choose some, query, okay, and learning algorithm, what's the best he can do to, have uniformly small risk. So that's what we call the privacy level of your defense mechanism. Does that make sense to you?
What's the typical choice for this script attack?
Oh, so we're going to look at, for example, polynomial, okay, the linear model, okay, or non-parametric. It could be a holder class.
Well, we care about the accuracy of F star, right?
F star is the function we already learned. We pretend to be the truth, right?
Yeah, but here you pretend it's the truth, right?
Yeah.
In application, we have data, we want to use the best classifier or
Yeah.
best regression function.
Yeah.
So we care about the accuracy of this F star.
Yeah. So that's a very good question, and we discussed that in the work. So you can consider the case where actually F star, you are protecting is different from the actual F star. Yeah, there can be that discrepancy, but in this work, we treat the one you have learned, hopefully based on really large data set, is good enough. So therefore, you don't worry about discrepancy between this F star and the actual theoretical F star. Okay, make sense? All right. So that's the concept of model privacy, the privacy level. Okay, as you can see, the privacy level we want it to be large or small. We want to have it as large as possible because the larger means the risk, okay, of the attacker, okay. Whatever strategy he's using, query and learning, is still large, right? Therefore, you have protected your model well. Okay. Any question, concern? Yeah. Oh, you mean from economic perspective, how many queries? Yeah. 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 Very good question. So, right. So if we want, we can make the story, complicated, right? Especially from the sequential perspective. Okay. So maybe I sequentially, query, right? And then maybe I stop when I find, what I can build is good enough for my, attack purpose. That definitely is, future direction. Okay. But in this work, we just focus on, mostly focus on the case where we already know, how many queries, the person sent. And then we work on, what are good defenses, what are not. Does that make sense? So earlier we, motivated from an economic perspective, right, the cost. Then we focus on the risk perspective. And then we say, suppose N is already given. And then, how you should defend yourself. Okay. All right, so those are definitely important aspects for future work. Okay. All right. And if you achieve the maximum, pretty much that's the best defense, right? Called optimal defense. This is from the defender perspective, and you can also look from an attacker perspective. Then we call that stealing error. Okay. So you see here, what's the smallest risk the attacker can achieve when F star is in the class, and then because you don't know how the defender will defend, therefore we can allow the defense mechanism to be in certain class, okay? Because you don't know in advance, right? So therefore, as you can see, we are already in a kind of a game setting, but in this work, with sublinear work, we haven't really gone to the degree to understand from a game theoretical perspective, because it's really hard and we don't really know how to do it. So at this moment, it's still focused on the statistical perspective, as I already explained more. Okay. Any burning questions? Yes. That's the one. Okay. The attacker, right, sends the query, okay, whatever strategy, and then gets the response. Then you have many pairs, query, xi, and response. And then he will try to learn F star based on that data. So that is F and hat, okay, and following his learning algorithm. Okay. Any other questions for clarification? Okay, good. All right, so the overall goal for the two parties, attacker, of course, minimize the stealing error, and then for the defender, we want to maximize the privacy level under the constraint. The utility is not too bad, right? Otherwise, nobody's going to buy your service, okay? So utility constraint, then you maximize the privacy level. So that's the objective. All right. Okay, so let's talk about some specifics, okay? So you have a more concrete idea what we're doing. So here is a numerical field. So I want to consider a really simple case that hopefully numerically you understand what is going on. So we have a polynomial regression setting, okay? So F star is just the polynomial, okay? And if you don't do defense, that we denote that as M no defense, right? You just give whatever the actual F star value, okay? Then, of course, the privacy level is 0 because the person, once you reach the number of parameters, you exactly recover the model. Therefore, the privacy level is 0. So that's really bad. Is that clear? Right? Okay, so now, what alternatives can we do? Well, a number of possibilities. One is we do ID noising. So here we suppose ID noising is just like you collect real data, okay, yourself. Right? It's similar to the traditional learning framework. And you can also do the constant noising. That is at the utility level, right? Remember we have a utility constraint. I just add a constant at the utility level. Then everybody is shifted. Right? Everybody is shifted. So you have that bias throughout. Unless you have additional data, you can't figure out that bias, right? Therefore, you're going to suffer. Okay? So that's the constant noising. And you can also do long-range correlation noising. So instead of ID noising, you're going to introduce a dependence between the errors. Okay, long-range dependence. Okay, and or if you are more clever, okay, so here we have an order disguise, which I will mention a little bit more later. So you're going to add noise in a way to trick the attacker. So they will tend to fit higher order polynomial, and therefore they suffer much more. Okay, so those are the different defense mechanisms we are illustrating here. All right, and let's see what's going on from the graph. In the graph, we have different sample sizes on the x-axis, and then y is the privacy level. Okay, and we compare the different methods. As you can see, this is no defense, right? The privacy level is really bad. It's just 0. Okay, and for ID noising, which is this one, I'm tracking, it's not so good. Okay, it's not so good. It's decreasing to 0. And if we allow the errors to be dependent, then it's better, right? It has improved. But if you add constant noising, then it stays the same, because that bias the attacker cannot figure out, right? Because that's for everybody, okay? Unless he has his own data, okay, which is another related problem, okay? All right, and then for our new strategy, order disguise, you see, as the sample size gets larger, we can mislead the attacker even more, and then, the estimate becomes worse and worse, okay? So therefore, this illustrates, first, you need to defend, right? And second, at least in this case, you can mislead, okay, the attacker to not able to learn our model, okay? All right, that's a quick illustration. Okay, so now let's talk about the ineffectiveness of ID noising, okay? You see, in the traditional learning theory, right, we know that, if you have F star in a class to be learned, and then, whatever learning strategies, okay, you have small training error, and if you have a good control of complexity, that would imply, very good generalization error, right? That's the traditional learning theory. And if you follow this learning theory, then if you add ID noise, that would be, in the framework of traditional learning, right? And you would know that the privacy level would not be good, because the attacker can just use traditional learning theory to learn F star quite well, okay? Right? Because they can cancel out. So therefore, it's critical for us to introduce dependence when we add noise, to make attacker's job much harder. So that's our main message, okay? So now let's talk about effective defense in polynomial regression a little bit more concretely. Let's suppose the two function F star is a polynomial, piece order polynomial. And of course, the attacker doesn't know the order. And here we're talking about a specific, attacker learning algorithm. Okay, that's one case. You know or you guess, attacker is using a certain way to learn. So the way is a standard, penalized regression. Okay, so here the first part is just regular loss. Okay, and second part is penalization of the dimension. So larger models receive higher penalty, similar to AIC, BIC stuff. Perhaps many of you are familiar with. Okay, so therefore the attacker is using the data and this, criteria to choose the order and estimate the parameter. Does that make sense? So this is the learning algorithm of the attacker. Yes. So here we even gave them the liberty to know it's a polynomial. Yeah. For this entertainment. Okay. Yeah, but not necessarily in general. Yeah. Okay. Good. All right. Okay. So here, what do we do? Well, we're gonna, add non-ID perturbations. Okay. We have the, privacy, right? Level, okay, and utility level, okay, utility loss level, because you don't want that to be large, okay. And how do we distribute that? Because utility loss is the average over different cases, okay. So in this illustration, as you can see, the blue is the actual polynomial, order 2, relatively simple. But when we add noise, we're gonna have much higher values towards the end. Okay, and do some additional adjustments. Okay, so it's not trivial, but mathematically can be worked out. And then the attacker will tend to choose much higher order polynomial, and also that estimate turned out to be bad. Okay, turned out to be bad. Does that make sense to you roughly? Of course, it is. Yes, this is one-dimensional case for illustration. It will be complicated. Yes, definitely. Yes, this is for illustration. Yeah. Okay, so therefore, as you can see, we can devise order disguise mechanism to make the task harder for the attacker. All right, so here's a simple theorem, which I don't want to get into too much detail. Okay, but the main message is that if the tail of x is not too heavy, okay, and the utility loss is not too small, okay, then we can guarantee, okay, the privacy level to be a power of Kn. Kn is increasing to infinity times UN. Therefore, this story is quite promising. Why? Because you see, for given utility level, there is a multiplier of Kn to the some power gamma. Therefore, with this going to infinity, you are saying that you can make the attacker suffer tremendously, right? Okay, with your order disguise mechanism. Okay, all right, yeah. The attacker sent the X. That's what we call query. So that's totally decided by. Yeah, higher. Yeah. Yes, that's a very good question. So here you see the story we gave is that for a given learning algorithm. So if the attacker knows that you're gonna trick them, they may consider adaptive procedure. And how do we defend? Then that becomes the game kind of things. We haven't really dived into that much because we thought the framework we try to set up it's already complicated. We discussed quite a few years, and indeed those are valid and important things to consider. Absolutely. Okay. All right. So the theorem is a positive result here. And you can also consider high-dimensional penalized regression kind of things following similar idea. So here the idea is that, well, suppose we have a high-dimensional sparse regression, as Tony mentioned before. And our device is that we're going to add noise to trick the attacker to select the actually noise variables. Okay, we're going to do that way. And if so, they're going to suffer. Okay, so that's the idea. And here, again, the numerical illustration is that, the blue thing. So that's our misleading variable projection. So we try to make the attacker select unimportant variables, right, by introducing your noise in a clever way. And indeed, you have much better privacy level compared to other strategies. Okay. All right, good. Okay, so here is the image classification case. It's for the fashion MNIST, data. Okay, and again, the story is similar, and we have a way to defend our model. Okay, so basically we try to overfit, try to mislead the attacker to overfit the dominating class. Okay, in queries you can, because we can change the estimated probability in a systematic way to mislead them. Okay, and the graphs are very similar to what we already seen. I don't want to spend too much time. All right, now, so far we talk about defending against a given learning algorithm. Right, the person. Oh, sorry. Yes, here we continue to do that. The only difference is that we are defending against a non-parametric method instead of parametric method. Okay, and then we're going to dive into, defending against attacker whose algorithm we don't know. It's completely up to the person. Okay, so here we consider k-nearest neighbor, okay, as a learning algorithm used by the attacker. Okay, and nearest neighbor, the idea is really simple, even if you haven't heard of it, right? So basically, you just look at your neighbors and then either have a vote or average, depending on whether it's a continuous regression or classification, right? So very simple. Okay. So the f hat, as I said, in the regression setting is just average, of the neighboring, observations. Okay. All right. So, why it's not working? Okay. Oh, so there's a delay. So maybe there is an adversary trying to attack me for the presentation somehow. Right? Wait a minute. Let's try this. Yeah. All right. So here is the theorem. Okay. So we suppose the function f star is a Lipschitz function. Okay. All right. And the attacker, uses nearest neighbor. All right. And then let's understand the privacy level of the different mechanisms. Okay? Here it turns out that if you don't do any defense, then the privacy level can be very small, right? That's very small, but we don't know exactly what the value is. So if you don't add any noise, but you see exactly function value, right? But yet we still don't know. Based on the literature, we don't know whether there is a known result. Seems not. Okay, so we only have an upper bound. Okay, but this value is very small, so therefore it's bad to not do defense. And then for ID noising, okay, you see we have a UN, in the picture. Okay, in the picture. Okay, so it's better compared to, no defense. And if we have the constant noising, then that's exactly the same order as the utility loss. That's not surprising, right? And in this case, it turns out for the nearest neighbor learning algorithm, privacy level, okay, cannot be larger than utility loss. So that's a relatively discouraging message, right? Okay. So once you decide how much to suffer, okay, to the normal users, unfortunately, the attacker can learn to that degree. Okay, therefore, in this case, you cannot mislead them to the degree that they do much worse compared to your utility loss. Okay, so the message is that defense, first of all, is necessary, and actually, the constant noising is optimal among all possible defense mechanisms, and you cannot have larger privacy level than utility loss, unfortunately. Okay. All right. So now, suppose you don't know what the attacker will do in their learning algorithm, right? That's completely unknown to us. So in this case, again, no defense. We have the same upper bound. Suppose now it's supposed to be, same upper bound, okay, for the privacy level. And for ID noising, then it really depends. If the utility level is up to a certain level, then we have that earlier formula. But if it's too small, then it's pretty much go back to the no noise, as you can imagine. And now, one thing I emphasized, we need to make the errors dependent. So we have the long range dependence. So the first x1, we have epsilon 1. The second, we have epsilon 2, and so on and so forth, right? So we have a sequence of noise we injected to the response. So here for the errors, they are correlated. The correlation is I minus j to minus gamma. So when gamma is less than 1, that's called the long-range dependence. Why? Because the sum of the correlations is infinity. It does not sum. Therefore, that means the correlation is still high, even if I and j are far apart. So that's the meaning of long-range dependence. If we do that, then turn out the rate, in the interesting case will be worse compared to the ID noise. So indeed, introducing dependence help you to defend your model. Okay, so that's the result. Okay. All right. So now let's ask another question. Okay, so far we have utilized the ID noising. Okay, all right. So can we do a fixed design instead of a random design? Does that change the picture? Well, it turns out in earlier theorem setting, no, you can't. So ID, okay, XI query or fixed design cannot improve in terms of the rate of convergence. Okay, so that's believable. And another question is that we haven't figured out is sequential query. Okay, sequential query, you see, I send my first x1, and then I demand you to respond, right? And you give me y1 tilde. And now I try to see, whether I can decide where x2 is, right? Because I can use the information you sent. Okay, in the classification case, it's particularly true. In the place where f hat is close to half, right? I may figure out where those x are, and then I'm going to ask those x query. You see? So therefore, there is a potential that in this sequential query setting, you gain something, right? But we haven't figured out completely, whether it's possible to improve the rate of convergence. I doubt. I think it perhaps not, but we haven't proved the theorem yet. But you understand the issue, right? Okay, all right. So that remains a interesting problem. Okay, all right. How much time do I have? 7 minutes. Okay, all right. So I'm gonna finish soon. Okay. So here is a real data. It's sentence classification based on bird. Okay. All right. So we have data sets. Okay, and we try to have toxical and normal sentences. So therefore, it's a classification setting, right? A sentence is normal or it's really bad, right? Okay, which we want to mark out. Okay, and then here the model is the sentence bird. Okay, so you use fully collected neural network, neural network. Okay, so attacker. We actually consider different types. One is from kind of ID with the same distribution from the data on which the classifier is built. Okay, or you can use the surrogate data sets. So therefore, the X has a slightly different distribution, which is kind of covariance shift kind of setting. Okay, all right. So here is the output. Okay, we have. So the original classification accuracy, is about 90%. Okay, right? Okay, and now here we just look at the accuracy because that's the end goal, right? Okay, earlier we looked at statistical risk, which of course is important but not directly reflecting the performance that is intuitively more understandable. Okay, the bottom line here is that you see, well, we consider different query size, 1,000, 2,000, 5,000. Okay, and the utility loss also at different levels. Okay, right? You can have more, higher. Okay, and there are different strategies. Okay, and indeed, for our misleading shift. So I don't have time to talk about details, but it's something at the estimated probability level, we're going to have some shift around the boundary adaptively. Okay, so as you can see, the classification accuracy, for the attacker, which builds, a neural network model. Okay, same type of neural network model, the accuracy is much decreased. Okay, therefore you have successfully defended your model by this technique. But instead, if you use other methods, you may not be able to defend very well. And the upper column and lower column correspond to the case where the query is from the same distribution or from different distribution. As you can imagine, the accuracy will be different. Right? Okay, so that's the oh. No. By that we mean that it depends on the X. Depends on the X. So maybe not the right word, but that's the meaning. Okay. Very good. All right. So the takeaway message that defense is absolutely necessary. Okay. And also there are different ways to do the defense, but some ways are better. Okay. All right. So let me just do a quick summary. So we try to set up a framework to understand, model splitting attacks and defense, and we feel somewhat comfortable, it makes some sense. Although there are a lot of issues that we want to explore in the future. So one is that maybe F star more general, right? Especially for neural network. Those are the ones we really use. Maybe the class should be more, in line with the neural network kind of representation. And secondly, it's possible the attacker has side information. For example, if we do the constant noising, if the attacker collect the data on their own, and then quickly they know, oh, there is a systematic bias, and they can easily de-bias, right? And then you are doomed, right? So those kind of things we need to study as well. Okay, make sense? So another is that the inference of a query, as I already explained, if it's a sequential query, how much more information can be generated there? Can that lead to improved rate of convergence? Okay, right? So that thing we don't know yet. Another is the dynamic decision making. So it's more in the game setting, which seems to be more, and Professor Chen, of course, expert in okay, econometrics, leading expert. So there, yeah. So the defender is guessing, right? What kind of learning algorithms the attacker may use, and the attacker is guessing, what kind of defense mechanism you're using. Can we have the usual kind of game, a value of the game, right? And that kind of thing. But seems to be too complicated for us right now. Okay. So with that, I will stop here and thank you.
Thank you, Professor, for a wonderful talk. Any question for Professor, please? Any question? All right.
Thank you, Professor. I have a couple of questions.
Sure.
If I did understand, the defense strategy is to add noise to the model, right?
Yes.
Exactly. But for usual non-parametric regression problem, the noise is there. So we consider that the model already has a noise. So
Correct.
what is the difference between the classical regression model and the defense strategy? This is my first question.
Okay, so let me answer that question first. Okay, so the question is that in the traditional regression framework, we already have noise. And what is the difference between what we are proposing and that case? Indeed, in the traditional case, we have ID noise, or maybe, kind of time series errors, right, econometrics. But the main difference is that we are going to have dependent errors in a way that is complicated to hurt the attacker's ability to learn the function we try to protect. So therefore, it's intentionally very different from the traditional regression setting to mislead the attacker.
Okay.
Yeah.
My second question is about the noise. The noise, you say that you prove it that dependent noise is much better than independent noise.
Yes, in the settings we consider. Yeah.
But the added noise is still independent from the covariates, I think. The queries.
Yes. At this moment, yes, we considered adding the noise. In some examples, it's different. We have the dependence on X, but in most of the theorems we consider, I presented, the noise are not dependent on X. They are will be more. Yeah, will be harder, right? Harder for the attacker. Yes, yes, that's it. That's something we can work on more. Yeah. Yes,
exactly. This is what
yeah.
I guess. Yes. Maybe last comment about the polynomial regression. I think even if the attacker does not know that it's a polynomial regression, this is a comment to Professor Tony. He can use another basis, and yes, of course, but because a function can be expressed in two different bases. There is a connection formula between the coefficient series expansions. So does it matter if he knows if it's polynomial or not? So
well, if you just
I think
yes,
so.
if we naively use the traditional learning techniques, I would agree with you. If you change, even if they don't know its truth is polynomial, they may get a similar result. But as Professor Chen mentioned, if they use some robust technique or other techniques that reflect our way of adding noise, that's a completely different story, right? Okay. Yeah, then it really changes the convergence.
Thank you very much.
Okay, thank you.
All right.
I'm still thinking about the accuracy of this F star. So if we think about from the beginning of the problem,
Yep.
we collect data.
Yep.
We want to provide good service or accurate service.
Yep.
So my goal should be output an F star that's as accurate as possible.
Mm-hmm.
And you add another goal of making F star as hard to estimate as possible.
Because our service for the normal user, they just want our, response value to be close to the actual.
To the actual.
Yeah.
So here I understand in your framework F star is given.
Yeah, suppose you have, because you are in service, right? You already have that F star.
But if you think about the problem from the beginning, you don't have an F star. You collect data.
Okay.
You construct an F star.
Okay.
Then when you construct this F star, you certainly want this F star to be accurate.
Yes.
Just like in classical statistics.
And we have no problem with that.
Yeah, now we want F star to be as hard to be estimated as possible.
No. F star is given already. We try to modify the response so that F star cannot be easily learned.
Yeah,
so we don't change. Once the problem is given, you can't change the nature of star, right? F star is already there.
Yeah, but you have the freedom of providing different F stars.
No, we have a fixed F star.
Yeah.
For the service, right? For example, we try to predict whether a customer will buy products, right? So that probability function, that F star is already there. Based on huge neural network.
At the very beginning, you have different choices for F star. So when you choose an F star, you want this F star, or if you have two F stars, if they're of similar accuracy, you prefer one of them that's hard to estimate, to be estimated by the attackers.
Yeah.
But your F star should be accurate, because
that's controlled by the utility loss.
Yeah.
You see, that's controlled by utility loss, right? So utility loss has to be satisfactory to the customer. That's why the UN, in the theory, should go to 0.
So whether you provide perturbation or not, you still want the answer to be accurate.
Yes. That's controlled by the utility loss.
So there should be like a sort of a trade-off between the two.
Exactly. Yeah. Yes, indeed.
But in your current formulation, you have this soup over this script F, like polynomial or say of certain smoothness.
Yes.
It's not about the accuracy of F star. From the server's perspective or the service provider's perspective, you don't really care whether it's smooth or not. You care about the accuracy.
Right.
So, your script F should be consist of, say, all possible, say, regression functions that of certain accuracy level.
No, that can be, an alternative formulation, but.
So in other words, in the original formulation, I wonder whether it makes sense. In the original formulation, data is given. You collect the data. But you have the choice of F star. And you want your F star to be accurate. You also want your F star to be robust in terms of.
Oh, I see. So that's a different problem. So you want to go back earlier, right?
Yeah.
When you have the data, you try to, have a F star that is accurate, yet in a mathematically tractable way is hard to be attacked, right? That's what I think that's a wonderful problem to work on, but that's different. So in our setting, we suppose you are already in service, therefore you F star, but you want to go one step back. I think that's a great problem to work on. Wonderful, totally agree.
Okay, let's thank Professor Yang once again.